This lecture will cover the concept of what is a mole, something called molar mass, and just a little bit more about what is this thing called the mole. So the mole might be something that you've heard of before, might think of it as a ground rodent. You may have heard of it before in a science context, but what we're going to be doing in this lecture, I'm going to explain how the value of 1.0 mole was determined, where that came from, and then one of the tasks you're going to have to do in this is figure out how to calculate the molar mass of a given substance. And the molar mass is the mass of 1 mole. And we'll be explaining how all of that works. So, what is the mole? Well, mole is a term. It represents a number of things, meaning it represents how many things there are. Now, we use the mole for describing how many atoms are present, maybe how many molecules, how many compounds. Again, it answers the question, how many? And to, I guess, maybe familiarize with this a little bit more, there's lots of words that we use to describe how many things. For example, a dozen. A dozen equals some number of things, right? It equals 12 things, and it doesn't matter how many. It could be 12 dozen eggs, or sorry, it could be 12 eggs would be a dozen. It could be 12 elephants. It could be 12 whatever. As long as it's 12, it's a dozen. A couple? How many is a couple? 2. How about a ream? That's kind of an unfamiliar term. You might have heard of a ream of paper before. But how many pages are in a ream of paper? 500. So that's kind of an unfamiliar term. Here's another one, a mole, 1 mole. How many things, it could be anything, are in a mole? That many, 6.02 times 10 to the 23rd. It's a big number. But really, it's no different than a dozen. It's just a term to describe how many things are in a mole, right? And there's this many. Like I said, it is a big number, 6.02 times 10 to the 23rd. And the reason it's such a big number is because, well, atoms are small. So to get such small things into a mass that is a usable number, which is really why we're using it, had to be a big number. So a little bit more on the number, where that actually came from. Well, it was made up in a way, and there's nothing divine about 6.02 times 10 to the 23rd. It was a chosen number. It's also known as Avogadro's number, and this fine-looking fellow over here on the right, his name is Amedeo Avogadro. He was an Italian scientist, and so Avogadro's number is the same here, 6.02 times 10 to the 23rd. Unfortunately, or maybe fortunately, I don't know, he didn't actually discover the number. It was just named after him as a bit of a tribute, a bit of an homage to him. So Avogadro's number is 6.02 times 10 to the 23rd. And again, that quantity is a mole. So now, how did we get there? It's a little convoluted, but it makes enough sense. 12.0 grams of carbon-12 was measured. Okay, so we took 12 grams of carbon-12, and that was purposely chosen, and the atoms were counted. Okay, and they weren't exactly counted, like one by one, but it was determined how many atoms were present, and that number that they found was this, 6.02 times 10 to the 23rd atoms in that 12 gram sample. That was called a mole. Now, what makes that super useful for us now is that the numbers that we have on the periodic table for atomic masses can also be used as grams to represent 1 mole. And we're going to go through some examples of this. But really, this number is very, very purposely chosen to make the atomic masses on the periodic table translatable and to be also used as grams, which is very, very useful in doing chemistry calculations. So, molar mass, I've referred to this a couple of times. What is it definitionally? Well, it's the mass of 1.0 moles of a substance, so 1 mole. So if I was to count up 12, or sorry, not 12, 6.02 times 10 to the 23rd atoms, and I took the mass of that, that would be called the molar mass. It's the mass of 1 mole. Now, because every substance has different masses, right? Hydrogen has an atomic mass, say, of 1.01, or if it's H2, it'd be 2.02. That's a certain mass. Carbon has a mass of, say, 12, if it's, that isotope 12. There's still 1 mole, it'd be the same number of atoms, but it would have a different mass. So to make it a little bit more simple, let's think of a dozen. What is the mass of 1 dozen eggs? I don't know, right? But you can sort of estimate, right? The mass of 1 dozen eggs. All right? What is the mass of 1 dozen elephants? Different, right? But still a dozen. There's 12 eggs in a dozen. There's 12 elephants in a dozen. The difference is the mass. It's still 12 things. So when we're talking about a mole, we're going to be talking about that same big number of things, 6.02 times 10 to the 23rd, but they may have different masses for different substances. In fact, they will. So there's some other names that you'll just want to be familiar with. It's also sometimes known as the gram formula mass, the gram atomic mass, molecular weight, formula weight. There's all kinds of different names. I'm in general going to use the term molar mass to represent this. A visual here for molar mass as well. Take a look. You've got on the left here 1 mole of carbon atoms. It's got a mass of 12.0 grams of carbon. Now, how many atoms are in there? 6.02 times 10 to the 23rd. All right, here is sulfur. 1.0 moles of sulfur. The mass of this is 32.1 grams. So there's 32 grams here. How many atoms are here? 6.02 times 10 to the 23rd. It's the same number of atoms, just a different mass because it's a different substance. Mercury. Mercury is very dense and it's pretty darn heavy. This is 200.6 grams. And again, how many atoms of mercury would be there? 6.02 times 10 to the 23rd. And one more, iron. It's got a mass of 55.8 grams. But again, how many atoms? 6.02 times 10 to the 23rd. So in each of these samples that you see, you can tell that the sizes are different, the masses are different, but if we were to count the particles, it would be exactly the same, 6.02 times 10 to the 23rd. So that periodic table can be pretty darn useful for figuring out the mass of 1 mole. You just need to look at the atomic mass, which is the decimal number that's usually underneath the chemical symbol. So let's do a sample problem here. If I asked you to find the molar mass of water, which is H2O, how would you do that? Well, you take hydrogen, and you take oxygen. Now the atomic masses we're dealing with are down here again. It's going to be the decimal numbers. And you add up the mass of what's in water. So there's 2 hydrogens, and this is rounded to 2 decimal places. And then oxygen, again rounded to 2 decimal places, 16.00. There's only 1 of those. So if you add that all up together, you get 18.02 grams per 1 mole. So 18.02 grams equals 1 mole. So something to note, 1 mole equals this many molecules and equals 18.02 grams. So when I start talking about equal signs and units being equal to each other, you might think of unit conversions. So this is how we're going to be doing unit conversions, going from, say, 1 unit to another, from moles to molecules, or from moles to grams, or something like that. So next one, molar mass number 2. I'd like you to calculate the molar mass of calcium hydroxide, that's Ca, and then OH2 in parentheses. So I'd recommend pausing the video, seeing if you got this concept of finding out the molar mass. You're going to need a periodic table. But that said, pause the video, add it up, and see how you do. We'll pick it up in just a few seconds. So, molar mass. Find the periodic table, you add up what's here. Calcium. There's 1 calcium. The mass listed is 40.08 on the periodic table. Oxygen has a mass of 16. There's 2 of them. Now, Parentheses here can be a little tricky. Remember that this 2 gets distributed into both, because the fact that there's 2 hydroxides means that there's 2 oxygens and 2 hydrogens. So hydrogen there as well, 2 times 1.01. And so you take all this together, add it up, and you should get a molar mass of 74.10 grams calcium hydroxide. And again, here's what this means. In 1 mole of calcium hydroxide, there are 6.02 times 10 to the 23rd particles, and also in 1 mole, there are 74.10 grams. So we have 2 ways of being equal to a mole. A mole can be equal to a number of particles, which is this. That number doesn't change. So 1 mole will always equal this many things. But we can also be equal to a mole in mass. Okay, so 74.10 grams is equal to 1 mole for this substance. Not for really any other substance, but for this one. So every substance is going to have a different molar mass. And again, you just need the periodic table to calculate that and add it all up. So to recap here, what is the mole? It's a number of things. It asks how many things are in a mole. That's a big number, 6.02 times 10 to the 23rd. And then also, we looked at molar mass calculations, how to find the molar mass of a given substance, which again is the mass of 1 mole, the mass of 6.02 times 10 to the 23rd particles. So that's it for this mole concept. Pretty straightforward, I guess. We'll do practice in class and get to it. We'll be doing more conversions in the next lecture. Now, a multi-step conversion. So we barely got through these conversions, but through those one-step ones, but the multi-step ones are necessary. And this is actually what we're going to be spending most of our time on is chemistry. In chemistry, that is these multi-step conversions. And so when do you need them? Well, when neither unit in the question is a base unit, so you don't have a simple prefix conversion, or you don't have a direct conversion. You're going to have to set up kind of like a tree of conversions to get you there. So how you can dissect or how you can determine whether you need to do a multi-step conversion or not is if you read the problem and you're given no base unit, but you're given 2 prefixes instead, you're going to need multiple steps, and I'll show you one as an example. How many millimeters are in 10 centimeters? So millimeter, centimeter, there's two prefixes there. Here's one, here's the other. So the base unit is meters. Because you have two prefixes, you know that you're going to need multiple steps, because even though, looking at the prefixes above in your notes on that first slide that we had, there's no straight conversion from millimeters to centimeters, or you may not know that one exists. So you're going to have to do multiple steps. So how do you do this, these multiple steps? First, you convert to the common unit. You convert to the base unit, because you could do centimeters to meters, and you could do meters to millimeters. So the meter itself, the base unit, is the common link. So first, convert to the base unit. Then from the base unit, get to the desired unit, or that, the one that you're asked for in the problem. Now the nice thing about these conversion fractions, the T-charts that we set up, is that you can do it all as one big step. It's going to look almost like a railroad track. And I'll show you what on the next slide here, an example. So here's the problem. How many millimeters are in 10 centimeters, the one from the previous slide? Base unit is meters. So that's what we're going to convert to first. Start with the number in the problem. Set up your first conversion fraction. So this is just converting to meters. One-step conversion, not too big of a deal. Centimeters cancel. So centimeters are gone in a way. Now this is basically just converting from meters to millimeters now. It's a one-step problem now. We just have to do one more. So we have one additional conversion fraction. Notice that you have meters here and meters here, so now those cancel. These numbers here make it true that there's 10 to the third millimeters in 1 meter. So if you look at all the red, everything that's canceled, anything that's left, you've got a number, number, a number, this unit, and this number. These two units are gone. So let's deal with the numbers first. 10 times 10 to the third divided by 10 to the second. So that's 10 is like 10 to the 1 times 10 to the third. You add those together, so that'd be 10 to the fourth divided by 10 to the second. You can subtract the exponents and get 10 to the second millimeters. Notice the jumping off unit here, it's this last one, that becomes our unit in the answer. So two-step conversions, again, are when you're going from two units that maybe don't have a common link between them, or they can't go straight to one or the other. So here's another example, kind of similar in a way, you'll notice. I'd say pause the video, see if you can do this. This is going to be the last practice problem, so you want to make sure to get it done and see if you can handle it, and we'll be doing more in class. But take a look, see if you can do it, pause the video. So here we go. Start with the number in the problem, 2.5 centiseconds. Convert to seconds using this. Then convert from seconds to milliseconds. Dealing with the math, the numbers, because all the units are gone here except for the one we want, because it says how many milliseconds. That's what we're trying to get to. So you got 2.5 times 10 to the third on top, 2.5 times 10 to the third, and then what is in the bottom is 10 to the second. So it's 2.5, and then 10 to the third divided by 10 to the second is just 10 to the 1. So 2.5 times 10 is going to be 25 milliseconds. What you might notice is that conversion, this practice problem right here, looks exactly the same as the one we did before. And that's because the prefixes are the same. So you're going from a centi prefix to a milli prefix. So these two-step conversions, they can, once you learn the system and once you learn the prefixes, a lot of these conversions are going to look very similar. And I know that this is going to be one of the more challenging lessons, but with some practice we'll get it done. To recap, we looked at base units and the metric prefixes, at least some of the common ones. There's a bunch more. We then learned the concept of dimensional analysis as a skill. where you have conversion fractions and then you're multiplying by 1 times 1 times 1. And then finally, unit conversion calculations. So that's going from one unit to another, using dimensional analysis properly, and being able to change languages, change the language of units. And so that's going to be it for unit conversions. We're certainly going to do some practice in class to get there, and then we'll build on this in later lessons.